the musketeers of Rembrandt's Night Watch, the interiors of Vermeer, and the swamps of Mondrian. What does the future look like for these masterpieces? Within the layers of paint applied many years ago lie chemical phenomena which affect many of these artworks. These alterations have attracted the attention of scientists and conservationists alike for the past 2 decades. The Rijksmuseum in the heart of Amsterdam invites visitors to browse one of the most prestigious collections of art in the Netherlands. One can admire masterpieces from the Dutch Golden Age, the vibrant colors of Van Gogh, and abstract selections of modern art. But under closer inspection, the visitor might discover fragments, cracks, and crevices not originally intended by the artist. These signs of deterioration are being closely studied by scientists to better define optimal conditions for conservation and ensure the longevity of these pieces.
The way that a painting was made, let's say 300 or 350 years ago, and then the way it looked at the time is different the way it looks now. The problems that we have to solve is that not only to understand how was it painted, but also to look ahead. How will it be in 100 years from now? And again, if now changes, eminent changes are taking place, and that we can research, that would be of very great help for the people after us. This change is something that we have to monitor. And before we can monitor it, we first have to research it.
In order to identify deterioration in certain paintings, the Rijksmuseum launched an investigation in the heart of their restoration workshop. Here, paint and chemical specialists study the health of canvases from a variety of collections. They must develop a precise diagnosis before diving into an intervention, retracing the entire course of the long history of each painting's conservation. In time, humidity or exposure to light could unleash mechanisms of degradation, specifically within pigments containing zinc or lead. Chemist Katrien Keune studies these phenomena which could drive some of these irreversible alterations.
Every pigment has its own story, degradation-wise. As I said, organic pigments degrade. But what we see a lot in painting as a red thread is degradation related to lead-containing pigment and zinc-containing pigment. And lead-containing pigment, where we see these small protrusions in paintings, or we see crusts forming on paintings. And related to the zinc, we see a lot of degradation forming with zinc white, where the zinc white is reacting with the pigment binder, and there you can also see sometimes protrusions, or for instance, the paint is flaking off because you see a poor adhesion. A lot of times the paint is still intact, but there are a lot of cases due to external factors that the paint is affected by degradation, and that's what we try to understand.
In order to give optical analysis a boost, the degradation study sometimes requires samples to be taken directly from the canvas. This painting from Rembrandt's workshop shows signs of alterations in clearer areas. The restoration teams will need to take samples from different layers of the painting in order to analyze their chemical composition and search for traces of deterioration. Optical microscopes reveal the formation of crevices and lumps which can develop quickly on canvas surfaces in response to chemical transformations in these pigments.
These kind of lumps usually are in the range of 100 to 300 microns, so it's something that you can see really clearly with a stereo microscope. What we don't know still are what are the major factors, how we can slow down the reaction, what are the long-term implications of these formations in the paint layers. At the moment I'm studying a painting where in one area of lead white you have these lead soap lumps and craters, and in another area of lead white you don't. So what's going on there? Is there something about the chemistry of the paint that actually expedites their formation in one area and doesn't in another? So these are some of the detailed questions we're trying to also to pursue.
Once collected, these precious samples are set within a transparent resin for analysis under a microscope. Patiently, the researchers must polish the resin to draw the sample of paint to the surface. The microscope's light reveals the different layers of paint applied by the artist along the canvas's surface. Particles of lead appear among some, moving from the lower layers up to the surface and provoking visible damage. Their concentration and distribution enable an initial diagnosis, but in order to dive deeper into these samples, the scientists need higher resolution images. To do this, we must travel to Saclay, near Paris. This is the home of the synchrotron, a particle accelerator able to produce extremely bright light, which enables a detailed look at our materials. This instrument has been used to study the photoluminescence of painting samples provided by the museum in Amsterdam. An ultraviolet ray is sent through the interior of the microscope, and the photoluminescence is captured when that ray bounces off the sample, a specific kind of reflection that reveals details otherwise impossible to capture.
In order to study these old, complex, heterogeneous materials, we're looking to collect the most detailed chemical and physical information possible. The light produced by the synchrotron enables us to carry out these studies even with extremely small samples. In the case of a painted layer, the pigment was mixed with a binder in order to hold its place once applied. Mixing an inorganic pigment with an organic binder could result in a variety of destructive chemical reactions between them. Unfortunately, that's what we've observed in the case of zinc oxides. What we're looking to understand is the nature of this interaction. What does it create? What obstructs it? And what could we possibly do in the future to prevent these things from happening to other paintings?
For 2 years, Selwin Hageraats has directed the collaboration between the Rijksmuseum and the IPANEMA laboratory of Saclay. The goal, an imaging process to study the alterations caused by white zinc when mixed in a binder. The mixing process, the acidity of a specific layer of paint, and even humidity are all factors that can contribute to triggering a degradation event from the zinc. Selwin is thus aging samples within controlled conditions to create models which could serve to establish future diagnostics of these works.
The paint samples are very heterogeneous, and we're trying to see why it is that some paint layers degrade very quickly, some paint layers remain intact. And we think it may have to do with how water diffuses through a paint layer, or also with the different types of pigment that are used in the different layers. One of the techniques that we like to use is photoluminescence microscopy, and this is ideal for zinc oxide or for zinc white because it luminesces very brightly, so we can nicely see the individual zinc oxide particles. And we've also found that some of the degradation products also luminesce, and this allows us to image the distribution of the degradation products at about a 200 nanometer scale or submicron scale. Another thing that we can maybe do is to look at the fluorescence of the pigment and predict how reactive it will be. We can tell what paintings are at highest risk and be able to tell what paintings specifically may need treatment. So we're hoping that maybe photoluminescence will give us this tool or aid that we can use in the studio to predict what paintings are at highest risk.
If science can't necessarily undo the damage caused by these deteriorations, it might be able to create the next generation of tools that will enable better conservation methods. That way, future art lovers can continue to marvel at these masterpieces of light and shadow.